Hi, everybody. John McElroy here again with Professor Terry Woychowski. I mean, I call
John,
you Professor. He's actually the president of Caresoft. We're back here to look at the 48-volt system that Tesla is really bringing to the market.
Yeah. You know, when Tesla came out, there was a lot of excitement for the vehicle for a lot of reasons. The stainless steel, body and steer-by-wire and everything. And, we couldn't wait to take it apart and learn more and more about those. But one thing intrigued me from the beginning was the understanding that they had moved to a 48-volt electrical architecture for the low voltage side. Because even though these things have 800-volt batteries in them, they still have what we historically called a 12-volt system or a low voltage side. And in fact, it wouldn't work without it. It's actually necessary in order for the whole thing to work as a system. Because you say, I got 800 volts here, why in the world do I need, a 12-volt system or a 48? Well, you do, so that the contactors can work. So the right things happen the right way in order to
well,
function.
you need to, the seat motors to move the seats
and then
the mirrors.
You have all those legacy systems that are designed to be powered by that. So the fact that they moved to from what's industry would refer to as 12-volt, although in the Model Y internally Tesla would call it a 15-volt system, low voltage, I was intrigued. And it was because of this. EV aside, the ICE automobile has needed to move to higher low voltage architecture for a long time. Back, when I was chief of GM's full-size trucks, I remember electrical guy, Matt Schroeder, come into my office. He's one of our subject matter experts here. But I remember he said, hey, this next model, we need to consider going to a 42-volt architecture. I was like, really? Why? And it was like, well, we're running out of juice. And historically, we just kept adding more and more and more electronic components, all of them demanding. And you get to a point where you say, hey, we have to start considering load shedding. If you want something on, I got to shut something off for you to get this. And then it was like, well, okay, well, what else do we get? Well, there's some benefits of doing that. Okay, that sounds good. How much will it cost? Discussion over.
It was too expensive.
Yeah, it was very expensive, because if you think about every lamp, every speaker, every motor, everything that's been designed at that 12-volt, now you're going to have to redesign it all. So it's extremely expensive. And so that Tesla did it was like, somebody finally broke this thing, and we'll see what comes after that. But they had the resource and the will and the capital and everything they needed to make an inroad. So I've been very personally interested in this for quite a while. It's electrical engineering, so you'll be on my depth real quick, but it is good. And just to understand basically why they're doing it, everybody's pretty much familiar with Ohm's law. Voltage equals your amperage times your resistance, V equal IR. Even I got that piece right. And then we look at the ability to do work, power, the power it takes to do work. Well, that equals this voltage times your current, your amperage. So if you want to maintain the same power and you can increase the voltage, the amperage comes down. So I don't need as many amps to do the work, because I have this.
So you don't need as much juice, is what you're saying.
Exactly. So if I need 48 volts of power, and I had 12 volts, like historically, that's going to require 4 amps. That's going to be 4 amps of power. If I have 48 volts, 48 watts, and I have a 48-volt system, now it only takes 1 amp. So it took me 4 amps. Now I only need 1 amp. So what happens is my voltage increased by 4 times. My current's reduced, to 25% of that. And the resistance in that wire, the cross-sectional area of that wire, because this amperage has gone down, it can shrink. So we can take those wire diameters down commensurately just because the voltage went up.
So you're talking take out a lot of weight, take out cost.
It's a lot of cost and a lot of mass, absolutely. And in a mechanical analogy, if you're a fireman, the guy who runs the pumper is called an engineer for a reason. You're controlling these things. You have an operator at the end of the hose. You don't want no water coming out. He can't do any work. And you don't want so much water coming out that he's flying around. You want to keep that steady. But the further away he gets, or the higher he gets, you have to adjust the pressure to give him the right output. Well, if he starts going up many stories, you know, he's losing because of gravity and the length due to friction. He needs a bigger hose. Or we'll just buy a bigger pump. You get a bigger pump. I can actually get a smaller hose. And that's what's happening here. So we've got a bigger pump, we've got more volume coming through, and so we don't have to have that big hose. We can make it smaller and smaller. And that's why you do it. I mean, that's you can do more work with less.
Okay, now we got some real world examples.
Here's a real example of that. What does that look like? This is a Tesla Model Y. You can tell because the mega casting's in the front and the rear, and there's no floor. So a pretty telltale style of Model Y. But the Model Y was at the 15 volt low voltage architecture. So we've laid next to its wiring harness, the Cybertruck harness, and this is where you get the current from. You get the voltage from the big battery pack. Mm-hmm. So remember last time we met, we talked about the transformers that stepped the 400 or the 800 down to these voltages. This one took a 400 volt battery down to 15 volts. And this is the wire. This plugged into that battery pack, and that's the size of the wire right there that fed the low voltage side. Now with the Cybertruck, we've gone from 400 volt to an 800 volt, but instead of 12 volt, we're going to a 48 volt. This is the exact same wire.
So pink to pink.
Yep.
Oh my gosh.
So this is what they had to do, and this is what they're able to do on this particular wire.
Yeah. And I'll spread that throughout a car, which has got
spread
miles
that
of
through
wiring.
A car with miles of wiring, and it starts adding up significantly. Mm-hmm. Yep. So that's the why do it. I mean, we've got the power, we've got the ability to do the work, and we can do it more with less. If we look pictorially here, the Model Y, that wire is aluminum. And so this is a depiction, if it's that size, if that was the size of the wire we just saw. If it were copper, it would be this size, because we can flow more current through copper than we can aluminum. Aluminum's got to be bigger if you're going to.
So the sort of gray is aluminum, the red would be the copper?
If that was replaced simply with copper, it would be that size.
Okay.
Because of the going from the 15 volt to the 48 volt, it's now this size. So you can see what we've been able to do. What we were doing there, now we can do here. Had it been here, direct comparison, you get about, on average, around 50% improvement.
50%?
Yeah.
That's significant.
Yeah. Now it can be different. 50% can be off by some, because oftentimes there's multi-strand wires, and so how many strands do you use, and how much space is in between each strand. So if you want the exact number, it depends, and I'd be glad to sell the data to you on what that is. But rule of thumb is about 50%. You can see there. Here's some more examples of the same situation. Here's the wiring harness used in the window motor. So just to raise and lower the window. And on a Model Y, it took 89 watts of power to raise those windows. In the Cybertruck, 96. So we have to do a little more. But if you look at the amps that are required to do that work, with the Model Y, it's 6.75 amps, but just 2 amps here. And so again, the result is, this was the wire in the Model Y. If that was the size of the diameter, this is what it is here. And you can see it right here. This is the actual wire on the Model Y, powering these windows. And then compare that to this little guy here, which is powering it on the Cybertruck. The insulation is actually thicker than the wire now.
That's impressive that, they're taking it down to something as skinny as that little wire. They're going for everything.
Absolutely. And again, like you said, small things over a long area, they add up pretty good. The heated seats. Well, heated anything from electricity means I'm just converting electricity into heat. In seats, you can see where that's done. On the Model Y, it's taken 116 watts. 122, the Cybertruck's actually using a little more to heat you. But again, the wires now go from, these are the wires that are heating the Model Y seats, front and back, the cushion and the seat, and then they're replaced with these little guys right here.
Man.
And so, you know, again, about if you see the change from the Y to the Cybertruck, again, shrinking. Now, there's a limit because it isn't just electrical current only that matters. There are other, you know, you can get this wire so small that all of a sudden mechanical properties start to rule. In other words, you can make a wire so small that just the normal vibrations in a vehicle will make it fatigue. So there are limits that you have to put in there just because of the mechanical properties of the wire. This is a big enabler, but it doesn't replace due care, good engineering, proper validation, you know, wisdom, experience, putting the whole system together. But
So what you're saying
it's a
is
heck of an
you just don't go 48 volt. There's a lot of thinking that goes into
There's
it.
a lot of work that goes into this and to do it well, for sure. Yep. This is the blower motor, and here's another real good example. You know, they're doing an almost identical amount of work, 318 watts, and you can see that there's 23 amps draw on the Y and 6.6.
Man.
Which allows you then to go from a wire that's essentially this diameter, scaled, of course, down to something about 50%. Had 4 square millimeters of area to 2.
Cut it in half.
Yep.
Really impressive.
Cut it in half. So we find that in harness after harness, and of course we do the total calculation of cost. How long are the wires, because the length obviously changes due to packaging and such things. So what's the actual mass, what's the actual cost delta? But you know, the rule of thumb, you can see, just apply that. This is always better than that if you're paying per pound.
Yeah, right, right.
The work's not done. This is interesting because the powertrain coolant pump, we have to, you know, thermally cool and heat these things. They don't like to be cold. These batteries, they don't like to be cold, they don't like to be hot, so we're always moving fluid. And so the pump to do that, you can see that with the Cybertruck, we're actually doing more work, 438 watts versus 386, but the wire's identical in this case.
Why so?
Well, it's work to be done. So they didn't do it all. There's still opportunity here. And you know, there's reasons why they would or wouldn't do it, but the wire that they use to do this is identical. This wire here versus the Model Y
Terry, do you think
versus
too,
the Cybertruck.
that they didn't do it? You know, there's that old saying, 2 designers or engineers put the pencil down. We've got to start building these things. So do you think they might have run into something like that?
I think that's probably the case. You ran out of time or you ran out of money.
Yeah.
You know, or you overlooked it, but I doubt that. I think it's more the latter, which is, okay, put the pencils down, time to go.
Yeah.
And it wouldn't surprise me. The way the company behaves is that you would see this change.
Yeah. Design change on the fly.
Absolutely.
Which they are the masters of.
They do that.
You know, one other
extensively.
thing too you didn't touch about is the 12 volt system, the RPM of the pump is much higher than on the 48 volt system. Less noise, less
That's right.
vibration.
Less noise, less vibration. It's, you know, had that been this, think of what this would then be. You know, it's driving more. So
Right.
balancing that whole system. And the NVH, or the cooling system, is a study in and of itself. These things are thermodynamic nightmares or challenges. But if you think the wiring is confusing, you look at the plumbing for these.
Yeah.
things.
Yeah.
And again, you know, some people, the plumbing can be quite complicated, and some integrate much better. You know, the materials you choose, how many bends. Every time there's a bend in a pipe, somebody paid for it. You know, nobody gave you those for free. And so the routing becomes important, how they're connected, and all these things are brought to bear. Here's just a depiction of the headlamps when you see the high beams, low beams, and then the wiring that goes to power the lamps. And this wiper motor, this monster wiper on the Cybertruck, there's two motors, doing this work. There's one doing this. So it's a pretty heavy motor to do the work, but again, you're able to do it with a smaller wire.
Really impressive.
So that's really kind of in a nutshell. You can see where they actually went to 48 volts because they didn't do everything. And remember, every part that runs on electricity has been designed and engineered to do something, and now you're going to redo it all. So it's a formidable task and a lot of investment. But unique to the Cybertruck, if it's a unique part, it gives you the opportunity to do it. If you share that part across your whole portfolio, it's harder to just change it here. You have to change it for everything until you're ready to do that.
You know what I love about this right here that you've listed is how much they went into the system to go to 48 volts, even though you said they didn't do it all. There's an awful lot here.
Yeah, and I'd say if it was unique to the Cybertruck, it was right on target, do it. Or if there's a big draw, a big current draw to where, hey, there's a lot of money in here because of the size, like that wire we saw. That comes right from the battery pack. That's a big wire, and there's a lot of cost to that thing. So those are where they did the wiper, the fans. When there's that tonneau cover, that's a big tonneau cover, and it takes a lot of power to roll that thing, especially if it's iced up or something. I did, by the way. It was full of snow and ice, and I was able to do it when I had it at my house. Pumps, and then modules. A lot of the modules have been converted to 48. So that's a big change because now all
That's
these
a lot of
PCB
engineering
boards and
work to
such
change
things.
all that.
But when you're going to do a unique module for this vehicle, that's where they did it. What remains at 15 volts, door lights, interior lamps, side view mirrors, park brake, and you can see, hey, they're reusing these parts in their other models, and so, hey, just carry those over. And then some of the modules have yet to be converted. So watch this space, as they go. They'll do this, but as they've invested here and now that tooling is in place and these suppliers are starting to make, these components that can handle these voltages, now you can see others moving. They should be seeing others moving in that direction because first principles wise, it's a good thing to do.
What you got here?
Well, you can also look at the impact of the 48 volts in these modules. And there's some unique things that they've done here. This is the left-hand body control module. So they have a left-hand body control module and a right-hand body control. It's how they've architected the electrical system in the vehicle, which is really important because it drives a lot of cost in assembly and
Well, they were the
everything.
first ones to go zonal.
Well,
right?
that was, they pushed deep into the zonal architecture, and, they were able to save, over a mile of copper wire as compared to some competitors. It's pretty amazing. And so with this architecture, they have a left and a right-hand body control module, and this is the front of dash, okay? Some people may have lovingly referred to it as a firewall. But, it's the front of dash. This is where the driver sits. This is interior. So this panel comes here and is, secured here to the A-pillar. So that's the front of the vehicle. And so this left-hand control module is where they're taking care of all the body controls, all the things that needs to do. But this is really pretty unique because here's the board that they're doing that work with. But one of the layers of that multi-layered board is a ground plane. And so these components are grounded to that, and then it is attached to this module directly. And then once that's in place, this covers it up. There's a gasket here. And at the front of dash, this is simply placed here. There's also another stud. We have to cut it off for our study. But as it's attached, it's automatically grounded. They cover two of these studs with a cap, and when they go through their LPO to give this training, the threads stay clean, take them off, put this on. You run it home, and that's it, you're done. It's grounded. Now competitors have, you know, several connectors that come in. Each one of these have a lead that come off of it for ground. And they come out, and they usually come, there's a weld stud, there's a lead, a ring terminal, you push it over the stud, you get a star washer, got the nuts, somebody drives them all. This one, you have to install it anyway, boom. It's in place, it's grounded. I don't have those wires, I don't have that labor, I don't have any of that work.
I love that stuff.
And very uniquely, the board is made such there's connectors on either side of the board.
Mm-hmm.
Connectors there and connectors here. So when this gets installed, now when you start doing the wiring harness under hood, it just
Plugs
snaps
right
on
in
here and you're going. And then the wiring harness on this side plugs in here. So where others have to fight, and by the way, this is a monster to get these wiring harnesses passed through the front of dash, and there's seals, and people are pulling them and pushing them and cussing, and you know, I wouldn't do the job. It's a tough job to do wiring the vehicle. This is just bolt this thing up, plug it in over here, plug it in over here, and no muss, no fuss.
They designed the hassle out of
They
it.
designed the hassle out of it. And really a clever way that they approached it, bringing cost out. You know, because you want to make these vehicles affordable.
Yeah.
They have to get great performance, they have to get great range, they have to be affordable. And if the customer doesn't know, doesn't care, not willing to pay for it, you should really consider not doing it, you know, and running all these ground planes where they're not necessary is a good example.
Mm-hmm.
This is a shot inside some of the body control modules, and the question that I had was, how do you get 48 volts down to 15? Because remember we saw the big transformers and says this is how you get from 900 to 48. Mm-hmm. Well, now I got to get this thing through the vehicle. Some of it at 48, some of it at 15. So how do you do that? And they really have two different methods that they employ. One is if you see that little chip right there?
That is a dinky little chip.
That is a dinky little chip. Don't ever ask me to put one in or take one out. But there's another one right there.
Mm-hmm.
Those chips and many others like it in different modules step that voltage down
So they're
to 15 or 5
they're
or
like
whatever
transformers.
They are. They're just a little bitty chip. So when you have a chip shortage, you know, they're for want of that little bitty wafer right there. Yeah. They have another method that they use. It's a different method, but right here in this array, you can see these are capacitors, a bunch of little capacitors and inductors, which really electronically add up to one capacitor and one inductor. But that's the methodology that they step it down to 15. So they're a couple different ways that they can approach that, and pretty unique.
Mm-hmm.
Why they do it one way and sometimes the other, it's a good question. I'm not sure.
Just the way it went.
Yeah. Here's a board. The guys pulled it aside just for you. They wanted me to present it to you and ask you if you could figure out, because your eyes for an Easter egg, what board that might be.
What's this little door here?
It's a door module.
Yeah.
That's the board for the door module, and I thought, John will like that. So,
Yeah.
when was the last
That
time
is
you'd see somebody
hilarious.
silk screen a door on a door module board? But
So they have fun.
they have fun along the way, so that's great.
That's really good.
So that's a snapshot of the 48 volt, what they did, how they did it. I think this is very significant. You know, the Cybertruck has its own significance and place in the market, but this really has legs.
So
and you can start to apply this now.
You know, Elon sent their 48 volt architecture to all the major automakers.
Yep.
What would your advice be to those companies once they get this stuff and decide they've got to go on this journey?
I'd say move fast, learn and move fast. You know, he did that. He sent that out, and it's self-serving, right? Because right now he's paying his volume for all these unique 48. Right. Well, if you all come in here, all these modules, all these motors, the price would come down. It'll come down for everyone, but so will the savings that you can now get system-wide. Right. So as soon as you're into the system, as soon as you're into your design and you're changing it, this would be the strategy you should be adopting quickly.
Yeah,
You know.
really good.
And I think, you know, that's the beauty of this vehicle, in that it is what it is. People love it, people hate it. You know, that's the market, and that's people. That's fine. But this is physics. And at the end of the day, this is part of what's driving the cost of this product. And can you afford it or not? And will people buy it? Well, if they can afford it, they'll want to buy it. If they can't afford it, it doesn't matter if they want to buy it or not. So I think this is really kudos to them. You know, this is a step. It took some boldness to do that. It took a lot of money, a lot of work to get it done, but looks like they were able to do that, and I hope a lot of people get to prosper as a result.
Well, Professor, thanks for the lesson. I'm learning a lot with you, man. It's really good.
My pleasure. Always welcome. We'll show you the next system next time around.
It's a deal.
Okay, excellent. Thank you.